Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the upcoming test. So we start off by learning the 4 operations. So you should know by now how to do long multiplication and long addition and subtraction. So let's look at some examples. So remember, for addition, you line up the numbers in the right columns and just add each column. 6 plus 2 gives 8. 8 plus 9 is 17. So I put down the 7, carry the 1. 1 plus 4 plus 7 gives me 12. So the answer here is 1,278. So if I wanted to do 792 minus 486, I again put them in columns, but here I need to introduce the concept of borrowing. So 2 minus 6 will give me a negative number, which we can't do in long subtraction. So we need to borrow. So we make this a 12, and then that an 8. 12 minus 6 is 6. 8 minus 8 is 0. And then 7 minus 4 gives us 3. So the answer is 306. We also need to know how to do long multiplication. So let's say we've got something like 464 multiplied by 52. Once again, we arrange it in columns. So what I do is I start by going 2 times 464. So 2 times 4 gives 8. 2 times 6 is 12. So put down the 2, carry the 1. And then I go 2 times 4, 8 plus 1 gives me 9. So 464 times 2 is 928. Now I've got to times 464 by 50. So I put down a 0 because the 5 is in the tens column. So then 5 times 4 gives me 20. Put down the 0, carry the 2. 5 times 6 is 30, plus 2 is 32. Put down the 2, and now I'm going to carry the 3. Change that to a 3. 5 times 4 is 20, plus 3 gives me 23. All right, now add these together. Basically what I'm doing here is I'm writing it as 464 times 50 plus 464 times 2, which is the distributive law that some of you would have learned. So let's add these together. So 8 plus 0 is 8. 2 plus 0 is 2. 9 plus 2 is 11. So put down the 1 and carry the 1. And 1 and 3 is 4. And then the 2's just there by itself. So the total answer is 24,128. Now let's look at order of operations. Please pause and copy down this slide if you need it. So here we have the acronym BIDMAS. I know some of you might have learned it as BODMAS, but it's essentially the same thing. It tells us the order in which we must perform operations. So as a simple one, if I have something like 4 plus 2 times 5, now notice here multiplication is above addition in BIDMAS. So what it means is I actually do this multiplication first. So when you're showing your working out, you work down the page, put an equal sign under. That equals 4 plus 2 times 5 is 10, which of course is equal to 14. Say you had something like 36 divided by 3 times 2. So it turns out multiplication and division are actually sort of the same rank because they're essentially the same thing. Same with addition and subtraction, as we'll see. So for division and multiplication, you actually do the one that occurs first from left to right, and same with addition and subtraction. So in this example, 36 divided by 3 plus 2, I would do the division first because it occurs first from left to right. So it'd be 12 times 2, which is 24. If, however, it was 36 times 3 divided by 2, I do the times first because it occurs first from left to right. So 36 times 3, 108, divided by 2 gives us 54, okay? So I'm going to rub off these examples and now show you some with brackets. So the reason that we have brackets is sometimes we want to change the order of operations. Sometimes I might want to do addition first. So if I have something like 3 times 4 plus 2, you do what's in the brackets first. The brackets are saying I want to perform the addition first. So that's 3 times 4 plus 2 is 6, which gives me 18. You might even have 2 sets of brackets. So let's say we had something like this. Well, what you do is the inner brackets first. So I'm going to leave the outer brackets alone. So I do these brackets first. Subtraction comes first. So 5 minus 3 is 2. Now I do the new brackets here. I do them first. So division and addition are both in the brackets. I do division first because it's higher in the BIDMAS chart there. So 12 divided by 2 is 6. So I have 4 times 6 plus 1, which is 4 times 7, which is equal to 28. So once again, I'm working down the page, and each line equals the line above. So that's my final answer. So now I'm going to take a moment to show you some questions involving this I for index. So again, please pause and copy down these examples if you need them. So when you have something written like this, we call this little number here a power, also known as index or exponent, and this is called index form. So what this means is you're timesing this number by itself this many times. So 4 to the power 3 is not 12. It's not 4 times 3. It's 4 times 4 times 4. You times 4 by itself 3 times. And this way here is called expanded form. So 4 to the power 3 is actually 4 times 4 times 4, which is 64. So what this index means in the BIDMAS charts is that I raise to powers. I do raising to power before division, multiplication, addition, and subtraction. The only thing that comes before raising to a power is anything in brackets. So for example, if I have 2 plus, let's say, 3 to the power of 3, so I need to do this one first because it's raising to a power. Now 3 to the power of 3 is 3 times 3 times 3, so it's not 9. So 3 times 3 times 3, instead of writing it in expanded form, I'm just going to write it as 27, so the answer to this would be 29. So let's have something like 2 to the power of 5 divided by 5 plus 3 in brackets. So brackets, whatever's in the brackets, is the only thing that comes before raising to a power. So I do this first. So I leave the 2 to the power of 5 as it is for the moment, divide by 8. So 2 to the power of 5 is 2 times 2 times 2 times 2 times 2, which is 32. So the answer is 32 divided by 8, which is 4. Notice I do raising to the power before division. I want to make sure we also know about squares and square roots too. So if I raise something to the power of 2, it's called squaring. So 5 squared, for example, that's index form. In expanded form, it's 5 times 5, which is equal to 25. So squaring something is timesing it by itself. Square root, which is this weird sign here, is undoing squaring. So if I say the square root of 64, I'm saying what number do you need to times by itself to get 64? And 8 is what you times by itself to get 64. Because 8 squared, 8 times itself, is 64. Square root of 81, for example, is 9. It's saying what number do I times by itself to get 81? So 9 squared is 81, so the square root of 81 is 9. Squaring and square rooting undo each other in exactly the same way that, say, multiplication and division undo each other. All right, we're now going to go on to factors, multiples, and primes, so please pause and copy this down if you need. We turn our attention to factors and multiples. Unfortunately, most people confuse these two. So factors of a number are smaller. They're numbers that go into the number, whereas multiples of the number are larger, counting up by that number. So these two are related. If one number is a factor of the other, then the other number is a multiple. So hopefully it'll make more sense when we see some examples. So let's say look at the number 12. So we're going to start by looking at its factors. Now every whole number greater than 1 has at least 2 factors, itself and 1. So 12 has factors of 1 and 12. So let's go up to the next number after 1, 2. Does 2 go into 12? Yes, it does. And 2 is multiplied by 6 to get 12. Then we go to the next number, 3. Is 3 go into 12? Yes, it does. And you times 3 by 4 to get 12. So then we go to the next number. We've already got 4 in our list. What about 5? Well, 5 doesn't go into 12 because if you do 12 divided by 5, you don't get a whole number. In other words, if you count up by 5s, you won't get 12. You'll go 5, 10, 15. You'll skip 12. 5 is not a factor of 12. The next number, 6, is already in our list, so we can stop. These are all the factors of 12. So if I wanted to write the multiples of 12, I can't write them all because they go on forever. Now, please make sure you listen to this because some good students are going to mess this up in a test. 1 is not a multiple of 12. I will never ask you for the multiples of 1, so never ever put 1 in your list of multiples. The first multiple of 12 is 12, so we count up by 12. So 12, 24, 36, 48, 60, and so on. It goes on forever. Okay, now let's look at the number, say 15. Okay, so for factors of 15, we need to find numbers less than or equal to 15 that go into it. So again, it will always have at least 2 factors, 1 and itself. So let's try 2. Is 2 a factor of 15? No, 2 doesn't go into 15. If you do 15 divide 2, don't get a whole number. So next number is 3. So 3 goes into 15 and is multiplied by 5. 3 times 5 is 15. So then we go to the next number after 3. 4, well 4 doesn't go into 15. 15 divided 4 is not a whole number, so I will not put 4 on my list. The next number, 5, is on the list. So I have all the factors of 15. So 12, as you can see, has more factors. It has 6 factors, whereas 15 just has 4. So the multiples of 15, 1 is not a multiple. It goes 15, 30, 45, 60, 75, and goes on forever. So we also looked at lowest common multiple and highest common factor. So the highest common factor, so you know what highest means and you know what factor means. Common means that both have it. So the highest common factor of 12 and 15 is the highest number that is a factor of 12 and also a factor of 15. It is the highest number in both lists, which in this case is 3. So the lowest common multiple, which I'll call LCM, is the lowest number that is a multiple of 12 and also a multiple of 15. So if we go to our list, now we look at the green lists, we want the lowest number that appears in both lists, and that happens to be 60. There's no number lower than 60 that appears in both lists. So that is the lowest common multiple. So if you're asked to find highest common factor or lowest common multiple, just list the factors and multiples of this number. So now we're going to go into prime numbers. Please pause and copy this down if you need. So I told you on the previous slide that every number greater than 1 has at least 2 factors, itself and 1. But for some numbers, these are their only factors. So numbers like 2, 3, 5, 7, 11, 13, 17, and so on. There's infinitely many primes. These numbers are all prime because they only have 2 factors, itself and 1. 2 is only divisible by 2 and 1. It has no other factors. 13, its only factors are 1 and 13. No other numbers go into 13. So if a number's not prime, we say that it's composite. So once again, there are infinitely many composite numbers. So, for example, 4 is a composite number. It has factors of 4 and 1, but it has another factor, which is 2. We saw 12 and 15 on the previous slide. They have more than 2 factors. They have factors other than themselves and 1. 24, for example, that would be a composite number. It has a factor of 2. In fact, 2 is the only even prime number. Okay, so that's what composite means. Now, 1 is neither prime nor composite because 1 only has 1 factor, whereas prime numbers have exactly 2 factors. So if you want to see whether or not a number is prime, you need to determine whether it has factors other than itself or 1. Now we're going to look at prime factorizations. So once again, please pause and copy down if you need. So it turns out for any number greater than 1, it will either be prime or we can write it as the product of primes. We can write it as a whole heap of primes multiplied together because product means multiply. So the way that we learned to do this was using factor trees. So I'm going to show you 2 factor trees really quickly. So I'm going to pick the number 30 and I'm also going to pick the number 72. So we want to write each of these as the product of prime numbers. Neither of them is prime because they have factors other than themselves and 1. We know that because they're both even. Both will have a factor of 2. So what we do is we find factors of each number. So 30, you might choose 6 and 5, 10 and 3, or 2 and 15. We will get the same answer no matter the factors we start with. It wouldn't matter if you chose 10 and 3 or 6 and 5. We'll get the same answer. So we write as 2 times 15. Now, 2's a prime, so we stop there. 15 is not, so we need to factorize it. So it factorizes as 5 times 3. So in prime factor form, we will get 30 equals all of these times together. 2 times 5 times 3. So 2, 5, and 3 are all prime numbers, which is why I stopped there. And I multiplied them together to get 30. Easy as. Let's do the same for 72. So we can find any 2 factors of 72, say 2 and 36. 2's a prime number, so we stop there. 36 is not. So let's write it as 9 times 4. Again, it wouldn't matter if you wrote it as 6 times 6 or 18 times 2. It doesn't matter what factors you use, we'll end up getting the same answer. So then 9 is not prime, so I need to write it as 3 times 3. 4 is not prime, I factorize it. Now I've just got 2, 2, 3, 3, 2. 2 and 3 are prime numbers, so I can stop there. So in prime factor form, I write 72 as 2 times 3 times 3 times 2 times 2. But I showed you about powers earlier. 2 times 2 times 2 is the same as 2 to the power of 3. That means I times 2 by itself 3 times. And 3 times 3 is the same as 3 to the power of 2. So this is how you write it properly in index form. 72 is 2 cubed times 3 squared, or 8 times 9. But see, there's only prime numbers. 2 and 3 are prime numbers. So you can actually use factor trees to find the highest common factor. So what you do to find the highest common factor is you circle the common factors and multiply them. So 2 occurred in both trees, so we're going to have a 2 circled. 3 occurred in both, so we're going to circle 1, 3. We can't circle any more of these 2's or 3's because there was only 1 in the other tree. So the highest common factor of 30 and 72 is 2 times 3 times the 2 numbers together that were circled, and you get 6. Note, it's not 2 times 2 times 3 times 3. You only use them once. We use 1, 3 and 1, 2. Okay, now we're going to quickly look at divisibility. So when we're saying, is a number divisible by another number, we're really asking, is it a multiple of that number? So divisible and multiple are basically the same thing. So let's say I have the number 3375, and I want to determine whether it's divisible by each of these numbers here. So when I'm looking at, is it divisible by 2, I'm saying, is it a multiple of 2? Or in other words, is 2 a factor of 3375? Please make sure you're familiar with the divisibility test in the textbook, in the notes. Let me know if you're unsure. So for 2, if we're checking whether or not a number is divisible by 2, we just need to see if it's even. Well, this number's not even because the last digit's 5. So this number's not divisible by 2. The divisibility test for 3 is add up its digits. So 3 plus 3 plus 7 plus 5. So if I do that, I get 18. If the sum of the digits is a multiple of 3, then the number is a multiple of 3 and divisible by 3. So clearly, this 18 is a multiple of 3, so yes, this number is divisible by 3. So the divisibility test for 4, check the last 2 digits and see if divisible by 4. 75 can't be divisible by 4. It's odd, so the whole number is not going to be divisible by 4. So the divisibility test for 5 is check whether the last digit is 5 or 0. In this case, it's 5, so the number is divisible by 5. Now we look at 6. So for a number to be divisible by 6, it needs to be divisible by 2 and 3. Well, this one's not divisible by 2, so it's not divisible by 6. Okay? Now, the divisibility test for 8, you look at the last 3 digits and see if they're divisible by 8. But this number is not even. No odd number is ever divisible by 8. So the divisibility test for 9 is similar to that for 3. You add up the digits, and if it's a multiple of 9, if the sum of the digits is a multiple of 9, then the number itself is divisible by 9. So 18 is a multiple of 9, so this number will be divisible by 9, or in other words, a multiple of 9. We could also check 10 too. To check if a number is divisible by 10, you just look at the last digit. If it's 0, the number is divisible by 10, otherwise it is not divisible by 10. Let's now look at the number 102,630. We're going to see, is this number divisible by 2, 3, 4, 5, 6, 8, 9, and 10, as we just did. So to check whether it's divisible by 2, look at the last digit. Yep, it's 0, so this number is divisible by 2. So the divisibility test for 3 was you add up the digits, so 1 plus 2 plus 6 plus 3. We don't need to add the zeros. That gives us 12. 12 is also a multiple of 3, so this number is divisible by 3. Now to check if it's a multiple of 4, we look at the last 2 digits and see, is 30 a multiple of 4? No, it's not. So this number is not divisible by 4. So now to check if it's divisible by 5, the last digit is 0 or 5, so yes, it's divisible by 5. Because the number is divisible by both 2 and 3, it must be divisible by 6. So we look at the last 3 digits for 8. 630 is not divisible by 8. Another way we know this, if it's not divisible by 4, it won't be divisible by 8. Now we look at the sum of the digits again is 12. 12 is not a multiple of 9. So this number, though it's divisible by 3, is not divisible by 9. And finally, 10, that's an easy one to check. The last digit is 0, therefore divisible by 10. So I know I went through this really quickly. Please let me know if you need any help with divisibility. We're now going to go on to what we've done with decimals. Sometimes we'll get an answer and it'll be a really long decimal, like 0.623, 623, 623, and so on. Goes on forever. We don't want to have to write heaps and heaps of numbers after the decimal point. That's tedious. So what we do is called rounding. What we do is we write a number that's very close to our answer but doesn't have quite so many decimal places. What we do is we identify the critical digit, and I'll show you how to do that in a second, and we use this rule. 5 or more, raise the score. 4 or less, leave the mess. So these are the rules we're going to follow. So we're going to look at rounding this number here to a certain number of decimal places. So sometimes you'll be asked to round to 0 decimal places. That is the same as finding the nearest whole number. Sometimes we just don't care about the decimal, which is part of a number. We just care about the whole number. So in this case, the first digit after the decimal place is the critical digit. 5 or more, raise the score. So this is 5 or more. So what we do is we go back 1 and raise the score. So to 0 decimal places, this would be 1. I raised 0 to 1 because the critical digit was 5 or more. So let's say I was asked to round to 1 decimal place. So for 1 decimal place, now the second number after the decimal point is the critical digit. So 2. So 2 is 4 or less, so we leave the mess. What that means is we take the second digit and all subsequent ones and we just leave them. We get rid of them. So to 1 decimal place, this is 0.6. So now let's look at 2 decimal places. So 2 decimal places, now the third number after the decimal place is the critical digit. Again, 4 or less, leave the mess. So we leave everything there, and it will be equal to 0.62. So if I was asked now to do to 3 decimal places, then the fourth number after the decimal place is the critical digit. So that is now 5 or more. So we raise the score. So what we do is we raise the previous number to a 4 and then get rid of everything else. So 3 decimal places, it would be 0.2624. We've round up because it was 5 or more, raise the score. So let's look at a slightly harder example. Let's say I had the number 0.12999. So, raising this to 0 decimal places is easy. First number after the decimal point is 1. 4 or less leave the mess. So this would just be 0. I just cross all that out. Let's now say I wanted to round it to a few more decimal places. Let's say I wanted to round it to 3 decimal places. So now the fourth number after the decimal place is 9. 5 or more, raise the score. So I want to raise this 9 here, but that would make it 10. So in this situation, what I have to do is raise this one to 3 and make that one a 0. So to 3 decimal places, this is actually 0.130. So if I now want to raise this to 4 decimal places, a similar thing happens. The critical digit, 5 or more, raise the score. I can't raise this one, I can't raise this one, so I have to raise this one. So to 4 decimal places is 0.1300, okay? So just so we note, when we're rounding decimals, we're not finding an equal number. So 0.1300 is not equal to this, but it is the closest number with 4 decimal places to our original number. All right, so the last thing we need to look at is place value. We actually looked at place value in both whole numbers and decimals. So the idea here is we want to represent heaps of different numbers, really large and really small. We don't want a symbol for every single different number. Imagine if there was a different symbol for 1,000,000 and for 900,000 and for 3. It's too much to remember. We arrange our numbers in columns, and you probably already know that with whole numbers. So when we're looking at whole numbers, we can go forever into the left direction. So I'm just going to go a few columns. So we have thousands, then hundreds, then tens, then ones. Then we have a decimal point. We also have columns after the decimal point. We have tenths, hundredths, and thousandths. So a tenth means 10 of them make a whole. Similarly, a thousandth means that 1,000 of them make a whole. So let's say we have this number here, 2796.153. So in expanded form, I know that's a bit ambiguous. We had expanded form with powers, but in expanded form, what we have is 2,000 plus 7 hundreds, plus 9 tens, plus 6 ones, plus 1 tenth, plus 5 hundredths, plus 3 thousandths. That's what this number actually means. 2796.153 means there are 2 thousandths, 7 hundreds, 9 tens, 6 ones, 1 tenths, 5 hundredths, and 3 thousandths. So this again is expanded form, and it tells us the place value of each digit. So 2 is a digit. The place value of 2 is 2,000. So 2 in the thousands column means 2,000s. The place value of 7 is 700, and so on. The place value of 5 is 5 hundredths. Place value of 3 is 3 thousandths, and so on. So when you're asked what is the place value of, say, the number 3, you need to give one number. In this case, I'd write 3 thousandths. If I was asked the place value of the digit 9, 9's in the tens column, so it means that there's 90. 9 tens is 90. So place value allows us to compare numbers. It allows us to see which one is bigger. So let's say I have numbers 4.235 and 4.532. So both of these numbers have the same digit but in a different order. So which one is larger? Well, both of them have a 4 in the ones column. So the place value of 4 is 4. Now we go to the next column from the left. So if we look at this column here, the tenths, this one has 2 tenths, whereas this one has 5 tenths. And obviously having 5 tenths is more than 2 tenths. So what that means is that this number here is larger. The number in green is larger. So what are the symbols we use? So we can use this symbol and this symbol for now. So the idea is the crocodile wants to eat the larger number. So which of them would we use? We use this one here. View it like a crocodile's teeth. It wants to eat the larger number. So pointing to the right, that means greater than. And pointing to the left means less than. So this statement says 4.235 is less than 4.532, which we know is true. You may also see these symbols, which is greater than or equal to or less than or equal to. I could insert that symbol, one of those symbols, in the above equation, make it true. If I put this line here, it now says 4.235 is less than or equal to 4.532. That is still true because they're equal to each other. So just a point about these symbols. 4 is greater than 4, for example, is not true. 4 is not greater than 4. But it is true if I say 4 is greater than or equal to 4, because they are actually equal. So make sure you're familiar not only with place value, but also the symbols that we use to compare numbers to see which one is bigger. All right, I'm sorry that this video has been so long. There is a lot to remember, but your teachers are here to help. You're a superstar. You will pass this test. So I'm giving out a lollipop to the first 10 people who watch this video and come to me in person and say, Elsie's is a soccer star. You do that, you will get a lollipop. So good luck studying. Again, sorry about the long video. This has been the luckiest maths teacher in the world. Have a great day.